we can start. All right. So you see the screen, Kiana?
Yes.
Okay. All right. Oh, good. Okay. So anyways, sorry for the technical difficulties. So it's always interesting. We've been doing Zoom for a lot of meetings, and we have our faculty senate, and man, a lot of other older professors do not know how to use computers. So I like to think I'm tech savvy, but who knows? All right. So anybody have any questions about anything now that we've started? Nope. Okay. So as we left off with chemical reactions, so talking about chemical reactions in general. So what affects chemical reaction? Concentration and temperature. And the reason for this is more collisions. I use the colloquial example. So let's say if I wanted to get a partner, and I mentioned this is my 7-year wedding anniversary, so I'm not really looking right now. But let's say I was single and I wanted to find a partner. Where am I more likely to find a partner? Somewhere that has 10 single people or 100 million single people. So, and the answer is 100 million, right? Because I'm more likely just to run into someone. Same thing with concentration. If there's more stuff, there's going to be more stuff running into each other. And the faster you're moving, the more likely you are to run into something. So that's the temperature. Temperature means kinetic energy. So temperature is average kinetic energy. That's how fast things are moving is temperature. So concentration and temperature means more collisions. Temperature is a little bit more complicated also because of the activation energy, which we'll talk about soon. And what we talked about before, catalysts, and we'll talk more about this later. They can either lower the activation energy or have more effective collisions or both. So, and also one of the things I want to impress upon you with science is kind of scary, how much we don't know. I mean, like here is the Arrhenius equation and K is the rate constant. And so K is equal to some pre-exponential term A times E Euler's number raised to the minus activation energy over R gas law constant times T the temperature. So I mean, this is a great mathematical equation, but what the heck is this A term, right? I mean, that is a semi-empirical model, right? We just took a bunch of data and threw it together and tried to make sense of it. And it's amazing how much science that is. We took a bunch of data, like, all right, well, this kind of works-ish, mostly, yeah, okay, let's go with it. And that's the basis for so much of what we know. And in a way, it's kind of scary. Has anyone ever heard of the Dunning-Kruger effect before? What? Yeah, Dunning-Kruger effect says that the less you know about something, the more confidently you speak about it. At the same time, the more you know about it, oftentimes the less confidently you speak about something. So that's known as the Dunning-Kruger effect. Have you ever known someone who's just in absolute knows nothing about a topic, but speaks so confidently about that topic? And then you have someone who just understands something forwards and backwards and then says like, well, it's kind of hard to say, exactly when the Hawaiian Islands were born. I mean, kind of, we have a fluctuation of like, we think 10,000 years could be a million years, and you're like, well, this person's like the world's expert. And you're like, how do you know? And someone goes like, no, Maui was formed, I don't know, 2.5 million years ago. I'm absolutely sure about it, and the question is like, who are you going to follow? A lot of people follow the person that's like, I know everything. That's the Dunning-Kruger effect, kind of, sort of, like where, and as you go forward in science, to me, it's kind of scary. Like, wow, this is what we know, and this is what it means. I mean, something as simple as friction, it's something that we're just kind of winged anyways, but we're doing the same thing with chemical reactions, and a lot of things we don't understand. At the same time, there's a lot that we do understand, and we know how to make it work. I mean, that's one thing, we know how to make it work. So, and with the, oh, and the pre-exponential, I mentioned this last time, the orientation times the number of effective collisions. And even that's not entirely true, because I mentioned before, like if you have this molecule, this collision doesn't work, but to form this molecule, you have to have a specific set of collisions. The truth of the matter is things can come here and they can dance and they can reorient. So it's one of those, we're still figuring it out. But we're getting there. But again, like I said, we can make it work. And I know briefly mentioned last class. So when we have, this is a reaction coordinate, reaction in progress, we have energy on the y-axis. So going up on the energy means higher potential energy. And the x-axis is reaction progress. Usually an internuclear distance is the reaction progress. Probably hydrogen, oxygen, internuclear distance is probably what I would read this graph as being the reaction progress. So you start off with hydrogen and oxygen very far apart, and then the molecules approach each other. When they approach each other, they're moving fast, and they approach each other, they start to slow down. Why? Because they're surrounded by electrons. Electrons are negatively charged. They're repelling each other, so they slow down. Their temperature, their average kinetic energy goes down, but their potential energy goes up. And then you reach to the activation energy, and then you reach the point known as a transition state. It'll be up here. And sometimes it's symbolized like this kind of double cross thing. I think it looks kind of like the cross Templar or whatever. That's the oftentimes we use for the transition state. And there could be more than one. There can be several. But then after the transition state, we have the products. And for an exothermic reaction, the potential energy goes down. So this is for an exothermic reaction, this height here, this is the amount of energy released. If it's endothermic, it's going to go up higher. And then this for like whatever distance here for an endothermic reaction, if the final energy is here, then that's going to be well, how much energy is absorbed. This as drawn is an exothermic reaction. And so, of course, like I said, you have reactants over here, products over here, and then we have this in-between state, the activation energy and the transition state going on here. So, and so the activation energy, so think of it kind of like, I think about this, I personally, I hate writing. I mean, just for me, do you guys enjoy, some people love writing. Do you guys like writing? Or anything? I mean, sure, story, but like a paper, like when you ever, like, do you like writing email? Emails are okay, they're short, but like reports, I hate writing reports. You know, and what? Yeah. Yeah, and you have to like psych yourself up, right, to write those reports, right? It takes energy, like to actually go there, and you have to like kind of bribe yourself, like, all right, if I write this report, I can, you know, watch another episode of my favorite show on Netflix or something like that, right? You know, of course, you know, I watched 3 episodes, I'm like, maybe I should write the report now. You know, that's procrastination. But I mean, you have to get like overcome this like energy barrier to like actually do it. And that's the same thing with chemical reactions. They have energy barriers to react, but that energy barrier is because they're surrounded by electrons or negatively charged. So it's rather than it's like, you know, our own minds and social pressure keeps us from doing something, it's actually steric interference. So it's the electrostatic repulsion of electrons that makes chemical reactions get over that barrier. And we even say that we kind of use this, at least I say it colloquially, like I could like kind of overcome a barrier to do something, like write a report. So you need that activation energy to react. So because that's the actual, for chemical reactions, it's a physical amount of energy that it needs to get through that electron cloud repulsion. And with temperature distributions, you have various amounts of things that have enough energy to react. And so low temperature, so denoted in blue, it's T1, and the other T2 has the red. There's a higher amount in the red, so that means that there's gonna be more effective collisions. So more effective collisions, well, actually collisions that have enough energy to react. So, and then I mentioned this in purple, that for very, very cold things, you can have chemical reactions like burning, like fire. So fire, definition of fire, if you're wondering, it's fire is defined as a rapid oxidation reduction reaction. So I mean, like we call the mitochondria the powerhouse of the cell. Does that mean that the mitochondria are on fire? The answer is no. It's not rapid, it's controlled. And this book right now is burning. It is burning from the oxygen in the air. Very, very slowly, but it's burning. Is it on fire? No, it's not. It's not rapid, right? So that's fire. So, but that's more of a colloquial definition, not a chemical definition. So the textbook that I'm holding in my hands right now, I put my iPad on top of it. I don't want to hold it up, but it's burning right now, but it's burning very, very slowly. And over 1,000 years, it'll burn to ash, right? But it's going to take a very long time. Why is it going to take so long? Because there's only a very small amount of molecules at 25 degrees Celsius, which is about the room temperature, that has enough energy to burn this textbook. So here's the Arrhenius equation, right? K equals pre-exponential A times e to the minus EA over RT. So if you take the natural log of that, the natural log of K is minus EA over RT plus, this is just one of the definitions, plus the natural log of A, right? Because if you remember the, so ln of A, oops, AB equals ln of A plus ln of B, right? And you can think of this one here as E to the ln of A minus EA over RT, if you will, because those do mean the same thing. But actually, no, maybe. No, that's right. That's right. But anyways, so you can write ln of K2 minus EA over RT2 plus natural log of A, ln of K1 minus EA over R, oops, T1, shoot. T1. And if you subtract those two, the ln's of A's go away, and you have the ln of K2 minus ln of K1 is minus A over R, T2 minus T1. And then you can turn this into that, right? Because when you subtract something, the natural logs, you get you divide them. So you can use this 2-point form, and you can see I kind of mentioned this before when we did the Clausius-Clapeyron equation in chapter 11, or no, 12, sorry, chapter 12. I was like, well, you'll see this again and again and again. So we use these equations quite a bit in this class. So let's apply for this problem. Consider this reaction between nitrogen dioxide and carbon monoxide. NO2 plus CO makes NO plus CO2. We found the rate constant at 701 Kelvin is 2.57 inverse molar inverse seconds, and that at 895 Kelvin is measured at 567 inverse molar inverse seconds. What's the activation energy? So I've kind of already hinted at this, right? So here is the equation that was just derived, and we have T1, K1, T2, and K2, and I just highlighted those. And you just have to put well, for me, myself, I like to do the math first. I mean the algebra first. So doing the algebra first. So you can move, we need activation energy. Actually, I can move this over more. So I can move R over here. So multiply both sides by R. And then I can divide both sides by this quantity here. It doesn't have to be in parentheses, but that, and I mean, get rid of that. And so that's how you solve for activation energy. So you just plug in the numbers then. Activation energy is R, 8.314 joules per mole Kelvin. ln of K2 567 all over 2.57 all over 1 over T1 1 over 701 minus 1 over T2 895. And so let's look at this in kind of, oh, and these are all inverse Kelvin. I should put Kelvins. So because of that, the Kelvins will cancel there, and it'll be joules per mole. So let's talk about numbers. We have number 701. That's smaller than 1 over 7 is smaller than 1 over 9. So 1 over 700 is small, is, well, 1 over 701. This entire number is bigger than 1 over 895, right? Because the bigger the bottom number, the smaller the fraction is. So like 1 over 2 is a bigger number than 1 over 1,000, right? So 1 over 701 minus 1 over 895, that's going to be a positive number. And so, and then here, this number here, so that's also going to be a positive number. So because 1 over 5, so 567 divided by 2.57, that's going to be about 200. And the natural log of 200, that's going to be about 40-ish, I'm guessing. So the top number is about 250. Bottom number is probably, I don't know, 1/10,000th. So if I had to, you know, I would guess 250-ish thousand would be what this thing is in that range. I mean, just like trying to do it in my head. And so if you put it in your calculator, and actually I didn't look at this, if you're wondering. That's just my Rain Man abilities. But I mean, you put it out and you get 145,000, and that's joules. That number is gonna be joules per mole. And then oftentimes I have it in kilojoules. Their action is in kilojoules per mole. So it's gonna be, how many sig figs? We got 3. It's gonna be 145 kilojoules per mole. That's what the activation energy is. We have 3 sig figs. Yeah. Okay. So, okay. Recap with this one. So we have chemical reaction. We have temperature and rate constant data for two temperatures and 2 different rate constants. We want to know what the activation energy is. So we take the 2-point Arrhenius equation and we solve for activation energy. We throw in the numbers in our calculator, and then we get an answer of 145 kilojoules per mole. Questions with how to solve this? All right, let's see if you can figure this one out. We have 600 Kelvin, the dissociation of ozone into oxygen and an oxygen radical. At 600 Kelvin, it's 3.37 times 10 to the third inverse molar invert seconds. And at 1200 Kelvin, it's 3.38 times 10 to the 7 inverse molar inverse seconds. So once you solve for the activation energy, as such. I know many of you are still in high school, but when I drink, I can't do math. That's one thing I lose my ability to do math. So I was like, that's I think I told you I just didn't. I took it easy yesterday. Only had chicken wings, no beer. So I can think. But then again, some days I'm just off. I'm not off today, thank God. Don't you hate those days when you're off? There's like no reason for it either. You're just like, I just can't think today. So one of the questions sometimes I get is which one do I pick for K1 and which one do I pick for K2? It doesn't matter. But for me, I don't like negative signs, so I always pick the lower temperature for T1, just so that the bottom number is not a negative number. So 4, 3.38, 7, 3.37, 600. All right, how many people think A? Who think B? Who think C? D. Okay, so half class is going for B. Although I just did my calculator, I got 91.9, but that is the right answer. So you guys just need more time, or are you guys getting calculators? Okay. So I mentioned about doing math in your head. So if you look at this is close to 10,000. So that's kind of 10 to the 4. And one of the ways you can do natural logs in your head, it's it's going to be 2.303 times the log of whatever it is, because the natural log of 10 is 2.303. So that's one of the change of base rules for logarithms. So the log of 10,000 is 4. So 2.303 times 4, it's going to be about 8. So you can say it's about 10. So it's about 10, and 8.314, this is about 10. So let's say this is going to be, yeah. So we have about 100 there. 1 over 600, these numbers actually work really well. So 1 over 600 minus 1 over 1200. That's I even picked these numbers so you could do it in your head. That fraction there is 1 over 1200, because 1 over 600 is 2 over 1200. So dividing by 1 over 1200 is the same thing as multiplying by 1 over 1200. So you can say that's about 1,000. So 100 times 1,000 is about 100,000-ish. So if you do kind of the stuff in your head, you should know the activation energy is close to 100,000-ish. So which means that these numbers there are likely, you could kind of rule out A because it's too small. But B, C, and D are valid. Anyways, anybody have any questions so far? That doing these calculations in our heads, I kind of had to do that. They kind of made us do that a lot at Berkeley. Like we had an oral exam, and professors would ask us questions, and we'd have to like answer them and like kind of come up with numbers on the fly. So if you ever go and decide, it depends on the school, of course. But if you want to go and get an advanced degree, that's one of the skills that you might have to draw upon. In some ways, it's really stupid, because when in the real world you have to do that. That's one thing that bugs me about academia, is that like we try and give you skills that have no application whatsoever in the real world. I mean, maybe if you're a surgeon, you would have to know how to, like, okay, well, I need to know how to on the fly, I need to know how to take out an appendix, kind of thing. But I mean, when else do you not have all the information? You can always look at the internet. That's stupid. Anyways, that's academia for you. So, okay, moving on. Reaction mechanisms. So here's another thing. This looks like, I mean, you can read it in your textbook too. To me, when I look at this stuff, I'm like, we are completely making this up. And yeah, we completely made this up. We're actually getting better at it, because now we can find intermediates. So they came up with this stuff in the 1960s, and they had no idea. And it was actually just a glorified hypothesis. And it turned out that our glorified hypothesis is correct. So at least it really seems to be correct. Although when we have reaction mechanisms, if you read this, you'd think that there's only one way chemical reactions can go. And that is not true whatsoever. So there are many, many different types of reactions that can take place. It's not like only one chemical reaction takes place. So, so what is that called? I think it's called the Maillard reaction. Are you guys familiar with that? That's the caramelization. Here I am cheating. I mean, here I am using Google. What's the Maillard reaction? Oh yeah, I was right. Yes. This is the reaction, the Maillard reaction. That's the reaction that makes caramel. So, in all the flavors. So like when you grill something, When you toast something, when you make toast, when you grill vegetables, meat, you kind of, you caramelize it. You get this kind of brown color and it has different flavors. So when you grill steak though, you're getting it's not just one product. We don't have a grilled steak molecule that we can say like, all right, if you eat this molecule, it feels like you're eating grilled steak. And this molecule, it's like grilled chicken. It's a whole bunch of molecules, right? So it's not just one. And that's how most chemical reactions work, is that you have many different products at various concentrations, some really small, some more than others. So, and it can be very, very complicated. But I mentioned though last class about enzymes. Enzymes are amazing because they give you one product and very specific products, and those are needed for our bodies to work. But anyways, going back to reaction mechanisms, and this is modeled after one reactant, one product, or sorry, one product from a set of reactions. But that's not really how it works. It's really in something as simple as you think like a flame. When you burn stuff, a flame, flames are extremely complicated. So it's not like, and you study fire. Fire is not just one product. I mean, you have, if you look at like a complete combustion, like, well, you have complete combustion where you form carbon dioxide and water. You can have incomplete combustion where you form carbon monoxide. But the truth of the matter is you get all sorts of stuff coming out. So fire, you get other hydrocarbons, you get various acids, and I mean, and you put something else on there like meat, and you start putting meat in fire, and you get a whole bunch of different reactants. So it's not like you get one thing. But we've modeled it and said, okay, we're going to try and simplify things. We're going to have a reaction mechanism, and it's the overall reaction, not just the steps. You have to look at all that, but the rate determining step decides the kinetics for the chemical reaction. So, and for a reaction mechanism, the steps and the reaction mechanism have to sum up to the overall reaction. And then the rate law that we predict with the reaction mechanism has to be consistent with experiments. And this means that we just made it up. And yes, we just made it up. But it looks like it works. Again, here I am talking, with the Dunning-Kruger effect. I probably sound so unsure. We know it works-ish, but we're learning more and more. So, for instance, if you have a multiple step chemical reaction, you can have the reactants form something, an intermediate, and then that intermediate then goes to form the products. And when you have the intermediate, you have different transition states for each. And which also means, we'll learn next chapter, reactions can proceed both directions as well. So that's another finer step. So, and then we predict, then when we write it out, I'll show you the rate law. We'll say, we predict this to be the slow step, and if it fits the overall reaction experimentally, then we say it's valid. And saying it's valid doesn't mean it's true. It just means it could be true. And back in the 60s, we had no way of determining if it was true or not. Nowadays, we can do spectroscopy and we can find intermediates. And then because of that, we're a little bit better. But then again, I think I told you, we have some reactions, we just have no idea. The Maillard reaction, no idea. We know it works. I know that if I turn on my grill and put on steak at 500 degrees Fahrenheit, I'm gonna hear I let it sit for, on low heat for the 15 minutes. I've got an awesome steak waiting for me, really flavorful. I know that reaction will work every time, but the kinetics of it, we don't understand. Just like my propane grill, the flames coming off of it, we got some idea. We're getting better, but it's a complicated issue. We don't entirely know. So this is what the textbook shows for the rate determining step, kind of like when you're going somewhere, you're trying to go somewhere, when you have like a traffic congestion. Once you get through that kind of congested point, then you start driving real fast again. So it's the congested point is like the rate determining step. I think of it like Thanksgiving dinner. So if I was making 100 Thanksgiving dinners, what do I have to worry about? Do I have to worry about the mashed potatoes? Do I have to worry about the cranberry sauce? No, I have to worry about the turkey. That's the slow step. The turkey is a slow step. If I want to have 100 Thanksgiving dinners ready, I better have 100 ovens. So because that's the slow step. If I have 5 ovens, it's going to take me a very long time to cook those 100 turkeys. So whereas 5 ovens, I could probably crank out enough mashed potatoes for 100 people with 5 ovens, not 100 turkeys. So, all right. So to give you an example of this, the book does not explain it very well, in my opinion. So we have this chemical reaction here in blue, 2 hydrogens plus 2 nitrogen monoxides makes 2 waters and nitrogen. And we found the rate law to be the rate is equal to some rate constant times the concentration of hydrogen times concentration of nitrogen monoxide squared. So where does that come from? So we're proposing like, well, what if we have a forward-backward reaction that's really fast, that 2 nitrogen monoxides form and deform dinitrogen dioxide. And what if our slow rate determining step in the middle here is hydrogen plus dinitrogen dioxide forward only, making water plus dinitrogen monoxide, and then dinitrogen monoxide plus hydrogen makes nitrogen and water, and we say this is a fast step. So the middle step is going to be the slow step, and we so since this is a slow step, you have to say that the rate law is determined by the elementary, and I guess the book does, I forget if they use the word elementary or not. It's not elementary, my dear Watson. It's the stoichiometric ratios. That's what elementary means for a rate law. So it means it's first order because there's a 1 here for hydrogen. It's first order for N2O2, dinitrogen dioxide. And so then we have our rate law is this second rate constant because it's there. And hydrogen, first order, and nitrogen, N2O2. I'm just going to call it N2O2 instead of dinitrogen dioxide. And that's our rate. But the problem is we don't know what N2O2 concentration is. So we can apply something called the steady state approximation. And the steady state approximation, that means when you have the steady state approximation, the concentration of the intermediates is constant. So then the intermediates for this chemical reaction, if you want to know what the intermediates are going to be N2O2 and N2O. So those are middle steps that disappear. So the N2O2 and the N2O, they are formed, but they're not products in a chemical reaction. So although it doesn't necessarily mean you could just have 3 of these floating around after the chemical reaction, and as the chemical reaction is going on, but you'd think, okay, why don't I just have all product? So then again, that's what I mean by you have many different side reactions going on. So but for that specific reaction, and for many reactions, you can, especially a simple one like this is a simple reaction. So believe it or not, like a flame is a very complicated reaction, but you will have different nitrogen oxides coming off of this too, though. But steady state approximation, intermediates are constant. That means the concentration of N2O and the concentration of N2O2 is constant. So even though it's being generated and consumed, so you say it's constant, and then the this reaction here, the top reaction, so you take this top reaction here and you apply the steady state reaction, meaning the forward reaction is going to be NO squared, because there's a 2 here, that's squared, K1 forward is that way. And then going in the opposite direction. So going in the reverse direction, you have K minus 1, and then you have N2O2, because it's just there, and it's first order. So then you solve for N2O2, and you get this, and you plug it back in to here, and well, actually not here. So this gets plugged into here, and then that gets simplified to that. So the book goes through this, and just so you know, I don't think the book explained everything very well. That's because he didn't explain really the steady state approximation. The other thing is, this is a pretty complicated problem for freshman chemistry. So you shouldn't, this is maybe a junior chemistry level. This would be like a hard junior sort of physical chemistry problem, or an easy graduate school problem. So I think this type of problem is out of bounds for general chemistry. So why am I talking about it? Because it illustrates a couple points. It illustrates what a reaction mechanism is and how they work. Am I going to have you do reaction mechanisms? Yes. And it's just going to be the slow step, and it's going to be elementary. I like to think that they're very easy, but I do put one in the next test, and it's if you remember that it's the slow step and it's elementary, meaning it's just the stoichiometric ratios. If it's 1, it's first order; 2, it's second order, kind of thing. I'll give you a hint, it's first order. You know, it's an easy problem. But we've gotten better at it. So this was the 1960s when we kind of came up with this. Nowadays, we can do spectroscopy. We can do spectroscopy, and we can find N2O2, and we can find N2O, and we can even look for these transition states. So we can find some of those transition states under certain scenarios using spectroscopy. So we're getting better. We're getting a lot better. And what we found out was that this kind of works-ish sometimes, but even seemingly simple reactions, like a flame, we have a lot to learn about it, and we're still learning more. And then something as seemingly simple as making caramel in your stove. Like, making caramel is kind of fun. You guys ever do that at home? Melt some sugar, put some butter in, it tastes good, you know. Making caramel, though, very complicated. We have a name for it, Maillard reaction, right? We have a name for it. Do we understand it? No. That's something we really don't understand at all. Grilled steak and caramel, no idea. So it's kind of scary in a way, how little we know, and something as simple as caramel. But caramel's actually, if you think about it though, caramel's very complicated because it's a mixture of things. And it's not just caramel. There's a lot of things we don't understand. I mean, we talked about drugs before. Cannabis. We have no idea how a lot of cannabis works, cannabinoids. There's a whole bunch of things we don't entirely understand. And like, if you see now that cannabis is becoming more and more legal, like they're starting to sell the pure products from cannabinoids. So they don't sell THC really anymore, but what is that stuff? I don't take it, so I don't know. But I've seen it being sold here. Gosh, I can't remember the name. It's not stevia. It's something, but stevia is. I know that's a sweetener. Sativia? I don't know. I shouldn't talk about this. I don't know my drugs. But they're cannabinoids, and that's something we just don't understand at all. Okay. Hopefully, I didn't scare you off with that kind of quasi-tight. Does anybody have questions about how reaction mechanisms work? The thing I want to impress upon you, it's the overall, so the reaction mechanisms have to sum the overall reaction. Rate law is consistent with experiment. It's a slow step, and that's when I test you on as a slow step. And you'll be given a much simpler reaction mechanism, and you just have to look at the slow step and then just write out the elementary, the stoichiometric ratio for the rate law. The slow, why is it called the slow? Because it's the slowest step. Okay. What's a slow step? So the Thanksgiving turkey doesn't work. Okay, so when I was a kid growing up, and I guess I'll tell you a little bit about my childhood. I think did I tell you guys both my parents were chemists? So yeah, so both my parents were chemists, and like I was inadvertently taught using chemistry metaphors. So I remember one time I was a kid and I was just taking my sweet merry time in the shower when like my family was trying to go somewhere. I forget where it was. It was like, it was somewhere proper, like, I don't know, like Easter church or something like that. And I was in the shower taking my sweet time, and my mother was getting annoyed at me, and she called and she goes, Michael, quit being the rate determining step. And so, meaning that I being in the shower everybody was ready to go, and I was keeping the family from progressing to whatever destination we wanted. Okay, so if you have a chemical reaction, there's always going to be some slow step that's keeping the chemical reaction from happening. So this formation, this formation here of N2O2, that's very fast. And once the N2O forms, it reacts with hydrogen. This is a very fast reaction. So the slow step is forming the N2O. So that's like me in the shower, taking my sweet time, keeping my family from going. So this is the slow step. And then the chemical reaction cannot go forward. It cannot happen until that slow step is done. My family could not leave until I was out of the shower and dressed and, out of the house. So no, that's given to you. You then, if this was an exam and I asked for the rate, the rate of reaction, you would then write as rate is equal to some rate constant, concentration of H2, concentration of N2O2. Both first order because there's ones there. That's the level that I want you to, and even that would be hard. That's the slow step will be told to you. The stoichiometric ratios, you write the elementary reaction using stoichiometric ratios. This is the, I guess elementary would actually, because it's already listed, would be K2. If it said this, you would put that. If this was 3, you would put 3. So yeah, Dennis. So as before mentioned, chemical reactions go both ways. How do chemists control the reaction in one way? So answer is it very carefully, and it depends. Are you talking, what are you talking about? Are you talking about a simple chemical reaction, like something in industry? You're talking about something biological? Oh, okay. How do oil companies make products they want? That is another difficult question, but I'm very happy to answer it. So an oil company, and so one of the problems about oil companies in the United States is that we have 50 states in the union, and we have 50 different laws with 50 different blends of gasoline. So different states have different laws. So I have to use a new page for this. So add page. This is not on the exam. So the answer in part is you have, the way that we make petroleum products is that we have a distillation column and we have oil. And oil is something that has many different products. Off the top of this, you get natural gas and also ethylene. So to make polyethylene, so you get something like, you get propane and I'm sorry, that's methane. Propane is 3 carbons, ethylene. The stuff comes at the top. You have the middle fractions, which is, this is known as naphtha. So that's going to be like 6 carbon range. Then we have gasoline, which is going to be 8-ish carbons. We have diesel, then jet fuel, then like, shoot, this is going to be fuel oil. And then the bottom is going to be asphalt. And this is just a very abbreviated one. Okay, so you have oil, you have one product, and oil is also a mixture. You're throwing a distillation column, and then a whole bunch of stuff comes out. So then, depending on the state, so Hawaii actually, well, most states, they turn their oil into about half-ish gasoline. We tweak our distillation columns here in Hawaii to make a little bit more jet fuel than most, because we have a lot of planes flying in and out of Hawaii. So we actually, as far as products, Hawaii makes a lot of jet fuel from petroleum. So then most places though look for gasoline, and they take some of these other, and gasoline, like they take either like these longer hydrocarbons, and so diesel is going to be in the 12 to 14-ish carbon range. 20, or jet's going to be, I don't know, like going to be 15 to 20. Fuel oil is going to be 20-ish. Asphalt's going to be like 100. And there's more. There's also paraffin wax is in there. But anyways, you can take these long hydrocarbons. You can do what they call cracking it, where you break the molecule at certain points. So you take like one long hydrocarbon, you crack it to form 3 smaller ones. And you can take one of those smaller ones, you can go called reforming it, where you cyclize it. And then you get different molecules from that. So we actually can get a lot more fuel out of petroleum now than we did many years ago. So that's but it's a very, did you want me to talk more about that, or is that, okay. They could typically crack it using zeolite. Zeolite is it's clay, and they oftentimes, you can reform it. Reforming is similar to that. You can also use that with platinum palladium. That's oftentimes used for that. So sorry if I'm giving you kind of a longer answer, but in a way, this is a difficult question, because petroleum is a heterogeneous mixture. It's not consistent, right? So it's fairly consistent, but not consistent. So you have a reactant that's a mixture that's not consistent. And then we have many different products. So petroleum, we have like, that's what runs our chemical industry, and our transportation industry is petroleum. So we have many different products. And you have also different levels of refinement too, like a lot of like cruise ships and a lot of not developed world uses a type of fuel called bunker. Have you heard of bunker fuel? It's kind of an unrefined kind of a fuel oil. Whereas we use fuel oil like in our trains in the United States, run off of fuel oil, but it's much more refined. So we don't have a lot of soot coming off of the back of our trains. If you've seen freight trains here in the United States, we don't have them here in Hawaii, but in the mainland, there's a lot of freight trains. And so, sorry if I'm giving you a longer answer, but that's kind of a complicated reaction. How do we control? Funny enough, we were talking about controlling chemical reactions coming in. Actually, me and Mr. Martin here coming into class, we were talking about that, because my undergrad's in chemical engineering. And the example I gave him was beer. Have you ever been to, I don't know how old you are, Dennis, so I don't know if you've been to a brewery, but yeah. You've seen the metal vessels, and they have, they're thick. They have the 316 stainless steel, and there's kind of thick jackets around the outside. So, huh? Yeah, when they make the beer, they make it in those big stainless steel vats, and it's a fermentation reaction. So they're taking simplified glucose and it's turning into alcohol and carbon dioxide. It's an exothermic reaction, and it runs best at 68 to 72 Fahrenheit. And one of the issues is how do, like, if you let it go, what can happen is it generates so much heat that it kills the yeast. So there's a couple ways you can do it. You can have smaller vats. I mean, like if you ever made beer in your bathtub, I've made beer in my bathtub before, like with a 5-gallon carboy. It's pretty easy to do. You can do that, no problem. But if you're making 10,000 gallons of beer, that's going to generate lots of sugar, that's lots of heat. You have to draw heat off of that. So how do you control the chemical reaction? One of the ways to do it is by heat. So the size of the vessel, this is one. You can, how big the vessel is. So how big you want to make the vessel. If you want to agitate it or not. So beer, they don't agitate it. So some chemical reactions you have, so what are they called? Propellers, agitators. I was thinking about propeller because they look like, to me, they look like propellers. You have agitators. Also in the chemical vats, they put baffling in there. You put these little, like, just pieces of blocks. I don't know. And what happens there is when you agitate the mixture, it creates turbulent flow and it mixes things more. That's what the baffles do. So you can, depending on where you put the baffles, how much you turn the chemical reactor, the agitators, what speed you turn them. So a lot of it becomes a fluid flow problem more than a chemical problem. And then you have the heat evolution. So in beer making, the jackets on the outside, they put usually propylene glycol in there and draw heat off, so you don't heat it up too fast. So I guess the other part of the answer to the question, it's contextual. It depends on what you're making. And with petroleum, there's many products you want to make, and depending on the state. So some states don't like the reformed chemical products. Some states don't mind them. So the distillation columns there make more of one or the other. Or Hawaii, we make more jet fuel. So, and then for another reactor like beer, so making beer, you have to worry about the heat evolution most. It's more controlling the heat for fermentation of simple beer and or wine. You're more concerned about the heat evolution killing your process. And in other ones, it's going to be a flow problem. It really depends. So sorry for the long-winded answer. I like to, as you haven't noticed, I like to give long-winded answers. So, but this class though is not dealing with control of chemical reactions. You can learn all about that in future classes if you want. So we're not going to talk it. We're not having you control chemical reactions at this level yet. And you probably won't have to do that unless you become a chemist or chemical engineer. So, other questions? All right, so catalysts. Catalysts provide an alternate path. They are not consumed in the chemical reaction. RXN is shorthand for a reaction. So we have two main types, maybe three if you consider enzymes. But homogeneous means same phase, heterogeneous means different phase. And of these two, the heterogeneous ones are the more powerful. The heterogeneous catalysts are very, very, very powerful. So, and I know we live on Maui, but we don't have many roads here on Maui. And I don't know how much time you've spent on Oahu, but let's say here in Oahu, you want to go from the airport to K Bay Marine Base. Okay, so the original way to do that, you would have to take this route here around the edge of the island there, around Oahu, and like no traffic. This takes you maybe hour 15 minutes, hour-ish, maybe hour and a half, 2 hours with traffic. I don't know how well you know the island of Oahu. Or you can jump on H3. Oh, all right. Sorry, Gianna, we're gone. Yeah, we should